Hi everyone. So as the next topic we'll see the introduction to Laplace transform and what are the Laplace transform application in the circuit analysis that we'll see in this chapter. So coming to the definition of Laplace transform, it is a powerful analytical technique that is widely used to study the behavior of the linear and lumped parameter circuits. Already you know what is linear, lumped parameter. So instead of transmission line, if you connect the same RLC in the lab, that will become the lumped parameter circuits. So for that we'll use this Laplace transform for the easy analysis. In earlier we have done the transient analysis in time domain. Instead of doing it in the time domain, we can do it in a different domain, that is nothing but S domain. If you apply the Laplace transform to that time domain circuit, it will convert into the S domain. From the S domain also you can get the similar kind of solution. We can get the I value or whatever the response you want to find out, that response you will get it. Later you can apply the inverse Laplace transform to get the response in time domain. This is another way of analyzing the circuit network analysis. So these are the useful in engineering, particularly when the driving function has a discontinuities and appear for a short period of time. That is nothing but transient, right? Whenever the switch is closed, open, discontinue in the current or whatever the response we used to get it. So for that it is useful. In the circuit analysis, the input and output functions do not exist forever in time. So we cannot keep it just like that. Always we no need to turn on, always we no need to turn off, right? Sometimes the application required continuous turn on and turn off, or sometimes we have to turn on and turn off the light or fan like that. So whenever we are using that applications, it experience the discontinuities. For that we'll use this analysis. For causal function, the function can be defined as f of t into u of t. To have the function only for t is greater than 0, we are considering f of t into u of t, because u of t will give the it will be considered only, it will exist only for greater than or equal to 0. So the integral for Laplace transform is taken with the lower limit at t is equal to 0 in order to include the effect of any discontinuity at t is equal to 0, because we are closing the switch at t is equal to 0 or opening the switch at t is equal to 0. That's why we will include the 0 also in this Laplace transform analysis. So consider a function f of t which is to be continuous and defined for values of t is greater than or equal to 0. The Laplace transform is then. So how can we find out the Laplace transform? If you know any function, how can we find out the Laplace transform? Means the Laplace transform of f of t, that f of t is function in time domain, it will become function in S domain when you apply the Laplace transform. The general definition is integral minus infinity to infinity. You need to multiply that function with e power minus st and integrate with respect to the dt. That means integral minus infinity to infinity e power minus st f of t into u of t into dt. So but like we said, we are doing it only for causal functions. That's why we are considering only 0 to infinity, integral 0 to infinity f of t into, anyway it is u of t. If you use, means you can keep this integral minus infinity to t, otherwise integral 0 to infinity f of t into e power minus st into dt. So what is here, it is nothing but f of t is a continuous function for t is greater than or equal to 0. It need to be multiplied with e power minus st, and which need to be integrated over the 0 to infinity with respect to the time between the limits from 0 to infinity. So this is what the Laplace transform definition. So the resultant function of variables is called the Laplace transform of the f of t. We'll see with the problems in the circuit analysis of S domain. So anyway, so as a next step, we'll see few basic functions or basic inputs. Like one is step input. If you take the step input in switching operations, there may be sudden or abrupt changes may occur in the current or voltages. On some functions, discontinuity may appear at the origin. That means at t is equal to 0, we may turn on and turn off the switch. The time the voltage may appear or current may appear, or current may 0 or it may reach to some other value. So to accommodate all these discontinuities mathematically, we can introduce or we can use this step or impulse functions. We'll see one by one. What is one is step function? What is step function means? If we consider the f of t is equal to k into u of t, if k into u of t is not exist, or that is if k into u of t is equal to 0 for t is less than 0, and k into u of t, that is f of t is equal to k for t is greater than 0, then that is called the step function. Mathematically we can derive the step function, or we can define the step function like the function which will exist for t is greater than or equal to 0 is called the step function. If this magnitude is 1 means, then that is called as a unit step function. And if you see that can be drawn like this pictorially, we can draw like this: f of t which will exist with the k magnitude for t is greater than 0, the constant magnitude k, and it is equal to 0 for t is less than 0. This is t is less than 0, right? It is the magnitude is equal to 0. That's what mathematical representation and pictorial representation. So if you closely observe that step function, the step function is not defined at t is equal to 0. Generally at t is equal to 0, what is the value, whether it is 0 or whether it is 1 or whether it is any other value. So to know that, we need to define the transition between the 0 minus to 0. That means around the 0 point, that is 0 minus and 0 plus. I am considering it is almost 0 only. 0 minus is less than 0, 0 plus is greater than 0. We assume that it is linear, the variation is linear, we can assume. Then hence k into u of t is equal to 0. K into u of 0 is equal to 0.5k. If you see here pictorially, from 0 minus, earlier less than 0 minus, it is 0 only. From 0 minus, it is starting with a linear variation, and at 0 plus, that is t is greater than 0, it should reach to the k magnitude. From 0 minus to 0 plus, we are assuming that it is varying linearly. When it is varying linearly, at 0 it will reach to the 0.5k. This is 0 and k means it is half of that highest magnitude, that is average, it is 0.5k. That's why k into u of 0 is equal to 0.5k. A discontinuity may occur at some times other than t is equal to 0 also. Always the switch is not closed or opened at t is equal to 0. Sometimes after some time at t is equal to 2 seconds, if another discontinuity may occur like that. So for example, in sequential switching circuits, the step function occurs at t is equal to a when a is greater than 0. That is a is equal to 2 seconds or a is equal to 5 seconds. So this kind of situations may occur in sequential switching circuits. So during that time, how can the step function will be defined and how can it be represented or pictorial representation? A step function occurs at t is equal to a is expressed as k into, instead of u of t, it will become u of t minus a. How means, we will see with that. K into u of t minus a is equal, as of now you can assume that k into u of t minus a is equal to 0 for t is less than a. Earlier here it was t is less than 0. If we keep 0, a is equal to 0 means k into u of t is equal to 0, t is less than 0. It is just similar to that k into u of t function, right? So if k into u of t minus a is equal to k when t is greater than a, instead of 0, if you replace the a is equal to 0, you need to get the previous equations. That's what we are getting. By substituting a is equal to 0, we can get the previous equations, right? These equations will get it, and we'll get the functions similar to like this waveform figure. So how can we represent this pictorially? Means at t is less than a, it should be 0. T is less than a, this a should be greater than 0. That means right side only you'll get it. The entire left side portion, it should be 0. When t is greater than a, it should reach to the k magnitude, and it should be like this. If a is less than 0, I have considered here a is greater than 0. If a is less than 0, the step function occurs on the left of the origin. The step function for a is greater than 0, it occurs at right side of the a value. If you take the a is less than 0, it occurs left side of the origin. Actually, if you take this as some 0, it should occur at left side of the origin. So the representation is, it is quite opposite to that step function, earlier step function, right? Instead of a minus t minus a, now it become k into a minus t is equal to k. Instead of 0, it will become k, opposite, just like this. And k into e of a minus t is equal to 0 for t is greater than a. Instead of having this 0 and k, here we'll get the k and 0. The step function is useful to define the finite width of pulse by adding the two step functions. Sometimes you may need to turn on, and immediately if you want to turn off means you can use the two step functions. So like this, for example, if you see, by adding these two step functions, what do you get? The common area is nothing but 0 to a, or if you take this step function like k into u of t minus 1 minus k into u of t minus 3. Actually by adding means generally it is k into u of t minus 1 plus u of 3 minus t. Actually if you see here, k into 3 minus t is equal to k, right? So this k into 3 minus t, I can write it like, instead of plus, I can take this minus of minus, that minus, if I send it inside, it will become t minus 3. So that's why it will become u of t minus 1 into u of t minus 3. So u of t minus 1 means it is right side, u of t minus 3 means it is left side. So we'll get the intersection region is nothing but between 1 to 3. It has a value between the 1 to 3 because by subtracting that both the waveforms, we can get the value k between the 1 to 3, and rest of the portion less than 1 and greater than 3, 0. So that's for the representation. Thank you all.